Linear motion is motion in one dimension, which is where we'll start. And so in this case, we're going to be working with frames of reference that are left to right. And depending on your preference, will either be right is positive or left is positive. In the initial case, we'll only be dealing with left to right or potentially up and down. But for now, we'll just speak on it in terms of left and right. This offers a little bit of confusion because of the variable d, right, which in most cases has been defined as distance. Right? Distance is the total amount traveled. This is useful when calculating a value known as average speed. Average speed is a non-vector, also known as a scalar value, that does not incorporate direction and therefore would not be dependent on the frame of reference. When measuring speed, we would use the non-vector notation for velocity, which would be v alone like this, divided by, equal to distance divided by time. In this case, the d represents distance. It's important to note that this distance is the total amount traveled. So an example would be if I started here and I traveled 70 meters to the right, and then I traveled backwards 40 meters to the left, the total d in this case would be equal to 110 meters and would be the value used as d when calculating speed. As I mentioned early in the year, we don't use scalar quantities near as often as we use vector quantities, which is why we're going to change this definition somewhat into average velocity. Average velocity is a vector and therefore contains a direction that would be dependent on your frame of reference. In this case, the notation changes ever so slightly so that we can identify velocity versus speed. So using v again, but drawing an arrow over top, we indicate that this is a vector quantity. This is standard notation for most courses in physics. Oftentimes in your textbook, the v's and the d's will be written in bold to indicate that they are a vector, but oftentimes we can't write in bold, and so we draw an arrow over top. I draw a half arrow simply so that the bottom half doesn't write into my letters, but you can of course draw the arrow however you're comfortable. Just be sure to not draw a bar over top, because in most math texts, if I'm measuring average, I would put a flat bar over top of this system. In physics, we try to avoid that so that there's not confusion. So anything that has nothing on top, right, we just leave this off of here, would be a scalar measuring distance and speed versus a vector measuring displacement and velocity. And in this case, d is displacement, right, which is also known as a change in position, or the distance from the starting point only. For our purposes, we will identify, especially in a left to right frame of reference, the change in position as the change in x, and so therefore I can say that displacement is the change in x. This brings up an important note in terms of notation. Change in x would be the final position minus the initial position as vectors from the initial state. And so displacement is defined like this classically using Newtonian notation. So this x sub 0 is often referred to as x naught, indicating my initial position. Right? Therefore, no notation, no subscript afterwards would be the final position. Some texts will utilize 1s and 2s or a's and b's to indicate final initials. So you can think of this as position 2 minus position 1. But in order to be somewhat more neat about it, we use the x naught and then no notation. Right? In a lot of cases, especially here at the beginning, these will be relevant values that will be given. But as we move further into the course, you'll of course be starting at 0, right? Because it makes sense to start at the axis. And so x naught will oftentimes be 0, which is why we can say the change in position is just a solo value above here. But do not confuse this d with the distance value in the average speed calculation. When measuring average velocity, right, this will be a standard formula that we'll use to derive a number of additional formulas in mechanics. The units of the values will be relevant, and so of course we're using the standard SI units, and so displacement as well as distance will be measured in meters. Sorry, this will be a brace with an M over the standard SI units for time, which will be seconds, making the units for velocity equivalent to meters per second. Be careful to note this meters represents meters, a measurement of distance or displacement, and not mass as a variable, which will come later. And as we move forward, the measurement of distance known as miles will be written as MI as a unit, so that you can tell the difference between meters and miles. Once we begin to move around, then it will be appropriate to measure the change in motion, also known as the change in velocity as a vector, which is a vocabulary term known as acceleration. Acceleration is a vector, and as such is dependent on vector characteristics. This is why we move away rather quickly from speed to velocity, because everything we'll be measuring will be changing motion in some way and therefore accelerating. And so as we define acceleration, it will be the change in velocity as a vector divided by the total time. This will be your second useful formula in conjunction with the v equals d over t formula for deriving a number of equations in mechanics. As we saw above, the units will be very similar. The units of velocity, writing units again, after this I'll drop those and just put units in braces. The units of velocity would be meters per second, as we saw above, divided by the units of time, which would be seconds, therefore creating a unit of acceleration of meters per second squared. The standard SI unit will be relevant throughout the course, and it's important to convert most of your given values into these units before you begin work. Using the same notation for the change in velocity, this acceleration formula can also be expanded, as we saw with the position, as v final minus v initial, or v naught, as vectors divided by the total time.